Hi everyone, myself Dr. M. Lakshmi Prasad, working as a professor in CSE in Institute of Aeronautical Engineering, Hyderabad. In this video, I'm going to discuss about the BFS algorithm, which is a graph traversing algorithm. So before going to see that, what is a graph normally? So a graph is nothing but a generalization of simple concept of set of dots, links, and edges and arcs. And here the graph should be nothing but a set of vertices and edges which consists of set of vertices. So that should be denoted by V and V of G, and then set of edges is going to represent E and E of G. So if I'm going to consider a graph, so in this graph, here the vertex set should be PQRS, and edge set will be, I can able to write PQ, QS, PR, and RQ. So these vertices, so these are the vertices, and these are nothing but the edges. So the other representation is that, so here I can able to write V of G, and the edges also going to represent it as E of G. Okay, so this should be the generalization of a simple concept which should going to be given in the form of sets, links, and edges and arcs. So here the graph may be the set of vertices and edges, so which is going to represent or denoted by vertex set V and it set which should be E. So normally, if I'm going to consider a graph, so graph is nothing but a collection of vertices and edges. So V should be nothing but set of vertices, and E should be the set of edges. What can I able to call it as a links? And here I can able to vertices. What can I able to call it as a nodes here? And here there are different types of graphs. So complete graph means that there should be an edge between every pair of vertices. So that should be a complete graph. So if there is an edge between for every pair of vertices, then it should be called as a complete graph. There are two kinds of graphs. What can I able to call it as directed graph and then directed graph. Okay. So normally I'm going to say this should be the example of directed graph. So what is this undirected graph means that the edges is not going to maintain any kind of directions, then it should be called as a undirected graph here. So whenever the edges is not going to maintain any kind of directions, so like this, then it should be called as an undirected graph. So what should be the meaning of directed graph? So directed graph means so the edges is going to maintain the directions here. So which one what we call as a directed graph. So whenever the edge is going to maintain the directions, then it should be called as a directed graph. So whenever the edges is going to maintain and does not maintain any kind of graph, then it should be undirected graph. So in undirected graph, the edges UV should be same as VU as well. So whereas in edges uh, in an undirected graph, so and in undirected graph, so the edges what are going to have that should be VU should be same as UV as well. Whereas in directed graph, so the edges UV may not equal to UV. Okay. And the directed graph is also called as a digraph. So where E should be a set of ordered pairs, and even if the edge V is present, the edge VU should be offset. Right. So let us consider here the edge. So V1 comma V4 may not be equal to V4 comma V1. Why? Because the edge direction is going to be there from this side. So the V1, V4 should not be equal to V4 and V1. So similarly, if I'm going to have the edge like this, so which is not going to maintain any kind of directions, then I can able to write. So v1 v4 should be equal to v4 v1, right? So the directed graphs are going to be drawn with nodes for vertices and arrows for the edges. And next one is that terminology. So what should be the terminology is that. So here the adjacency. What is the adjacency here? So the vertex V7 and V4 are said to be adjacent if there exists an edge between V1 and V8. So there is an edge. If there is no edge, then it should not be an adjacent nodes. So here V1 and V7 is not adjacent because there is no edges present between them. So the vertices V7 and V8 are said to be adjacent. And weight, what is the weight here? So the weight is nothing but a cost parameter that should be associated with each edge. And the path is nothing but the sequence of vertices. So V1, W1, W2, and so on, and where there is an edge for each pair of consecutive vertices. And the length of the path is nothing but the number of edges along the path is nothing but the length of the path, and the length of the path of n vertices which can able to call as n minus 1. So the cost of path is nothing but the sum of the weights of the edges along the path is nothing but the cost of the path. So the cost of the path is nothing but the sum of the weights of the edges along the path is nothing but the cost of. So these are the terminologies what are going to be followed here. So they have adjacency. So what should be the adjacency here? The vertex W is said to be vertex V if and only if that there exists an edge between them, and the weight is nothing but the cost parameter, so that should be associated with each edge. And the path is nothing but the sequence of vertices where there is an edge for every pair of consecutive vertices. And the length of the path is nothing but the number of edges along the path is nothing but the length of the path. And the length of the path of n vertices should be n minus 1. So how can I able to find the length of the path from V1 to V7? Well, I want to find the path from V2 to V7. So one should be minus 1 and minus, that should be 0, one of the case, and V2 to V5. So 5 plus 2 plus minus 2 plus 4 plus 1. So this is the under. So this is the path by what I can able to move from V2 to V3, V5, V5 to V7. Sorry, V5 to V3, V6, V8, and V7. So these and all will be the edges along the representing graphs. So here what I can able to do that is, so we're going to have a set of vertices 1 to n, and the adjacency matrix is going to be represents the graph, and Aij equal to 1 if there is an edge that should be belongs to edge set, and Aij should be 0 if does not belongs to edge set. So normally the graphs are going to be present in the form of vertices. So what can able to call it as an adjacency matrix here, and here I can able to consider, suppose if this is like a simple graph what I drawn. So then the rows and then columns would be that, and so the values here should be either ones and zero. So it should be 1 if there is an edge between the two vertices. Okay, so here in this case, so there is no self edge here, and there is an edge from A to B, so A to B should be 1, and there is no edge from, so that should be 0. Similarly from B to C I have edge, so it should be 0, and C to B. So like this we are going to fill this adjacency matrix. So here the value should be either zeros and 1 if there exists a path edge between them. If there is no edge, then it should be 0, and if there is 1, and if there is a edge between them. So let us consider this is the graph what I am going to have. So in this one, I'm going to consider the set of vertices along the columns and then rows. This is the rows, and this should be the column. So, so what is the edge I'm going to have from 1 to 2? So 1 to 1 it should be 0. So 0. So there is an edge from 1 to 2. So this should be the directed graph. So there should be 1, and there is directed graph. There is an edge from 1 to 3. So it should be, and there is no edge from 1 to 4. And 2, I'm going to I don't have the edge from 2 to 1. So it should be 0, 0. And 2 to b, I'm going to have the edge. So that should be 1, and this should be the 0. And for 3, there is no edge that is coming going from 3. So that's why what I'm able to call it as all should be the 0 in this case. And for 4, I'm going to have only one edge that is present 4 to 3. So that's why it should be 1. So this is the matrix what I'm going to obtain here. And another representation of the graph is that adjacency list. What is this adjacency list? So for each vertex V, there should be a set of vertices that should be adjacent to V. So I'm going to consider the edge 1, 2, adjacent of 1, that should be 2, 3, and adjacent of 2, it should be 3, and adjacent of 3, it should be 9, and adjacent of 4, it should be 4. So the variation can also keep the list of edges coming into the vertex. Graph searching. So graph searching is nothing but we are going to visit all the vertices of the graph in such a way that uh, the graph should be the directed one and that one. The methodology is that we have to be explore every vertex and then every edge of the graph. So how are going to be find out the vertex in a graph? So for that we have to pick up the vertex as the root and then we have to choose the certain edges to produce a tree as well. So that should be the graph searching. So in this, the first concept is that breadth first search. So what is this breadth first search here? So breadth first search is going to be explore the graph, so turning it into a tree. So for that, what you have to do, you have to take one vertex at a time and expand the frontier of the explored vertices across the breadth of the frontier. So build a tree over the graph. So for this, what you have to do, you have to pick a source vertex to the root and find then discover its children, then children should be etc. So explore the graph, so turning it into a tree, so one vertex at a time, and explore the frontier export vertices across this, and build a tree over the graph such that we have to pick up the source vertex and find its children there. So breadth first search is going to associate with the colors to guide the algorithm. Okay, so for this, the white colors is nothing but I'm not going to discover anything, and then the gray color vertices are going to be discovered, not fully explored, and then the black color vertices are going to be discovered and fully explored. So there are three types of colors what I'm going to apply. So white vertices, so these are going to be not discovered at all, and gray color vertices means discovered but not fully explored, and black color vertices are going to be discovered and fully explored. So BFS, so breadth first search is going to be considered in this case. So what I'm going to do that, this is the algorithm for that. So here initialize, first of all I have to be initialize the vertex and then make the queue here. So it should be store the starting vertex, and then when the queue is not empty, so what you have to do, you have to be remove the top element of the queue, and for each element that should be belongs to the edge, whether it is adjacent or not. So then you have to be take this what color it is, whether it is white, gray, and then black. Though then you have to be NQ by make use of NQ operation have to be uploaded into that queue. Then make the color as black. Okay. So this is the algorithm for BFS. So initially I'm going to take one word graph here. So in this graph, so first of all, what we have to do, we have to be check what are the adjacent vertices of the root. So then you have to be push onto the Q here, and then from Q remove the what should be the top element, and find out make it as a white means discovered and not fully discovered and not fully visited. So gray means partially and black means fully discovered. Okay. So initialize the vertex, yeah, every vertex, and then U should be the every vertex but only once, and V should be the every vertex that appears only in some other vertices that should be adjacent in the list. And total running time of this BFS would be before estimate of V plus E. So let us consider this example here. So this is the graph. So initially I'm going to make it as a infinity in this case. So I'm going to consider one starting source vertex. So that should be pushed onto the queue. So this one I'm going to consider as starting vertex, and this one is going to be stored in the queue here. So next, what I'm going to say, I want to find out what are the vertices that should be adjacent to S. So initially Q I'm going to have this S, they should be pumped out. And what are the vertices that are adjacent to S that should be R and W and then R. So this one is going to be pushed onto the Q. So I'm going to consider next W. So what are the W here? So for W, what are adjacent vertices? That should be T and then X. So these are the two vertices that are adjacent. So S, W is popped out. And what are the adjacent vertices for W? That should be T and X. So that's why what I'm going to do, that should be up and to the Q. And for next, I'm going to consider R. So what is the order that should be adjacent? That should be V. So S, W, R. So these are the popped out nodes in the queue. And for R, what should be the vertex that should be adjacent? That should be V. And then similarly, so what I'm going to say next, I have to what are the nodes that should be adjacent to T? I want to find it out. So what should be nodes that should be adjacent to T? That should be U. So U should be added on to the queue. And next one X. For X, what are the nodes that are adjacent? That should be Y. So Y should be added to the queue. And similarly V, so we already visited, so that's why I want to make it as a dark black. And next one is U, so for U what are the nodes adjacent Y, and Y I should also visit, it should be marked as black, and make the pies empty. So this should be the working of this BFS algorithm. So once again look at this. So the BFS algorithm, so we have to be find out the vertices that are adjacent to vertex and initialize the vertices. And then while Q is not empty, what you have to do, you have to be remove the top, and for each E that should be adjacent. So if the color is white gray, so then it should be NQ, otherwise it should be black. BFS, so initialize the vertices, okay, then make this starting source into the queue, starting node. So while queue is not empty, I have to repeat this. So remove the top element, and for each element that is adjacent or not, I have to identify. If it is adjacent, make it as a color white and gray. So once it is visited, then I have to make it as a black. So look at this. This is the graph what I'm going to have. So in this graph, so I want to mark this each and every node as infinity first. Then later on I want to make this as a source vertex. So that's why I want to make it as 0 in this case. And then I'm going to find out what should be the source vertex X, right? So for S, what are the nodes that are adjacent? That should be R and W. So these two will be considered. And from this one, So what I'm going to do, so what are the nodes that are adjacent to S that should be pushed onto the queue. Then later that, so what are the nodes that are adjacent to W that should be T and X. So those two things is going to be portioned to the added to the queue. And for R it should be T, so that's why I'm adding the queue. And for W I'm going to consider use this U as the new vertex. So that's why I'm going to consider as this one. And for this Y, so Y, what are the nodes that are adjacent to X that should be Y, so Y is also going to be added to the queue. Finally, I'm going to have only Q and V, so there is only one, so that's why it should be listed. Finally, the queue becomes empty. So like this, we're going to find out. So let us consider another example. So this is the graph what I'm going to have. So in this one, how I'm going to find out the BFS order? I want to trace it out. So initially I'm going to take this as the starting node. So A, from A, so consider a Q. So what are the nodes that are first we have to insert it. So what are the nodes that are adjacent to A? So that should be, you have to remove this, and B, C, D is going to be added into the queue, and this should be this starting vertex. And for B, so if I'm going to consider this as the B, so this is the next node what I visited. So what are the nodes that are adjacent to B, E, and F? So those two things should be added in here, E and F, and B should be removed. Next for C, so what are the nodes that are adjacent to C? So that is D. So D is already there. So remove from the queue. Okay. So next one is D. So what are the nodes that are adjacent to D? E and then A and C already visited. So what I am going to do? So D is going to be removed and add it to the queue. And here, so for E, what are the nodes that are adjacent? F. So F is already there. So remove from the queue. Finally F. So this is the BFS order of this graph. So which is going to be visited all the vertices exactly once. Right? Similarly, construct another graph as well. Another example. So A, B, C, D, E, F, G. So this is the graph I'm going to have. So in this one, so first I have to be push on to the queue, and then I'm writing the BFS order in this case. So from A I'm going to be starting, this should be the starting one. So starting one is A, and for A what are the nodes that are adjacent? So that should be B, G, F, and then H. F is not there. B, G, H. So what I'm going to do? So remove this and add the BFS order. So next one for B. So what are the nodes that are adjacent for B? C, H. So H is already there in C. So next visiting node is B. Then push on to the add it to BFS order. And for Z, what are the nodes that are adjacent? So that should be F. So add up to the queue. So remove the G. So next one is H. So what are the nodes that are adjacent to H? So C and then E is there, so that's why I'm going to add E in this case. And remove this H. And for C, what are the nodes that are adjacent? D. So D is not there, so add the D here. So I'm going to remove this. Next one is F. So for F, what I'm going to do, the adjacent nodes is E already there, so that's why it should be F. And next one is E. So E is also there, E and then D. So this should be the BFS order of the given graph, right? So like this, we're going to be traverse the each and every wedge in every vertex of the graph, and then can able to find the BFS order. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.